Okay, it's time to get started with some calculus. Before we can do the calculus concepts properly, we need to remind ourselves a little bit about function notation and the relationship between a function and a graph. That'll allow us to present the main problem that we'll be talking about first in calculus, and then we'll be in a position where we can start solving the problems. Um, when you do a graph, normally you think of a graph of an equation. The equation would typically be something that involves x's and y's with an equal sign. And the idea here is that this tells you a relationship between x coordinates and y coordinates. So we want to, we find a pair xy that satisfies the equation by saying that the x and the y value make the equation true. If you take an equation like that, you can make a table. So here's the equation. I can give myself a bunch of values of x, and then for each of those values of x, I can use the equation to generate the value of y that'll go with those. Notice that it's not essential that the equation looks like y equals a bunch of stuff with x's in it, but it does make it easy to find the y values if it's written that way. So we would say that the point -3, 7, x coordinate -3, y coordinate 7 would be a point on our graph. X coordinate -2, y coordinate 2 should be a point on our graph. And really, if we just generate a whole bunch of points, then we could just draw a bunch of dots, and we would start to see the shape of the curve. So this would be the graph of y equals x squared minus 2 by just drawing a bunch of dots. Now, obviously, this is just some dots. The real graph has all the dots filled in, every value of x. And so if you fill them all in, it looks more and more and more like what we would think of as a curve. So we can generate the individual points from the equation, but if you really think about generating all of them, then it will look like a smooth curve. So that's the idea of graphing an equation. What we tend to do in calculus and in pre-calculus as well is we use what's called function notation. So instead of using the variable y, we'll now use the notation f of x. And so instead of the y, we're going to use f of x. So the idea behind that is that for every x, there's a single y coordinate that goes with that x. And so rather than calling it y so that this looks like a different letter altogether, we call it f of x to emphasize the relationship that point has, that number has with the original x value. So instead of writing y equals x squared minus 2, we would write f of x equals x squared minus 2. And now we have this dependence of x and y, the x coordinate and the y coordinate sort of captured in our notation. So when you have a function like f of x equals x squared minus 2, you could say, well, what does f of minus 3 mean? This is our way of saying put -3 in for x and see what the y coordinate is going to be. So in terms of the graph, that means we're saying the x coordinate is -3. What does the y coordinate equal to? So this is simply what you do. F of -3 just means take this expression and change the x to -3. So that's all that's happened here. The term that was an x became -3, and then we just evaluated it and got 7. So the result is 7. So 7's the y coordinate that goes with the x coordinate of -3 on the graph. And if we go back and look at the graph, do I have that on there? Yeah. It doesn't really show up, but at -3, 7 would be there. That's not on my picture, but it's pretty believable that that point is up there somewhere. Okay. It's important in this class to not be too fazed by using letters instead of numbers. If we had this function f of x is 3x minus 2, then certainly f of 2 means put 2 in for x. But if someone wrote f of a here, then that really just means take that expression and change the x to a. That's all that's happened. If you see f of some god-awful thing, well, that means take this expression and change the x into whatever that god-awful thing is. So you have to be a little bit resilient to seeing letters and expressions. When we talk about the function notation, we really should do exactly the same thing if the input is an expression or has letters in it than we do if the input is just a number. We really should behave no differently in those cases. Here's a quick example of a modeling type problem, and this introduces a term that we'll see in a lot of questions in our book, the price demand function. The idea here is that from the basic theory of economics, we expect that price and demand are related to each other. So, so in other words, if you charge more for something, you'll probably sell less of them in general. So, so price and the number of things you expect to sell have a relationship. And so when we have problems like this, we'll see an equation like this. It'll be price equals some expression in terms of number of items. So the P here, which they've written P of X, they don't always do that. Sometimes it's just a little P, is price, and X represents the demand on the number of things sold. So the trick here, though, is that they're asking for the revenue function. And so we do need to know one thing about doing business, and that is your revenue from selling something is the price times the quantity that you sell. So this makes sense. If you sell, I don't know, 50 things for $2 each, then your revenue is $100. So it's simply a matter of saying that if you take the price you're charging for something times the number of them that you sell, that's how much money you're bringing in from that item. Obviously, your store or your business probably sells more than one thing, and there's also a cost of production. So we'll see problems later on that are more complicated than this by trying to be more realistic. But this equation, revenue is price times quantity, is going to come up over and over again in problems that involve a price-demand equation. So it's good to make a note of that and to remember that this is where you can look back to see it. As far as evaluating things, it's very easy to do because they gave us that the price function was 1,000 minus 5x, then price times quantity is just price times x. X is the quantity. So 1,000 minus 5x times x is the expression for revenue. And then once you have that, then it's just a matter of being able to plug in 50 items or whatever the amount is.